Volume hologram formation in photosensitive materials. The mechanism of volume hologram formation in photosensitive materials, a complex process where several components are involved, is starting from the interference exposure. Holographic recording induces a generally three-dimensional spatial modulation in the optical properties. The final grading features optical functionality that consists in specific diffraction of light, to be characterized by means of its diffraction efficiency, defined as the ratio of the input readout power to the diffracted power, as well as angular response and frequency response. Different kinds of gratings are formed, according to the specific recording conditions. While the geometry clearly determines dimensionality and size of the grating, many factors influence how the material responds to light during the holographic exposure. The material response strongly depends on intrinsic material parameters, such as material composition or viscosity, as well as on recording parameters, such as exposure duration and recording intensity. Volume holographic grating formation can be attributed to different physico-chemical material transformations, depending on the type of photosensitive material. In case of polymers, an interplay of polymerization and diffusion, induced by the spatially modulated exposure, is responsible for hologram formation. A light pattern is projected into the photosensitive medium, inducing local polymerization, proportional to the light intensity. Thereupon, a chemical gradient is induced, resulting in monomer diffusion and subsequent polymerization. As a consequence, the hologram is formed as a periodic modulation of optical properties, according to the recording light pattern. This grating formation mechanism is illustrated in Figure 1. Schematic illustration of grating formation in photosensitive polymers, unreacted polymer chains, cross-linker, dopant, for example, monomers, and photoinitiator are needed for the material composition and layer formation, top. Interference exposure induces local polymerization, middle, and subsequent diffusion of components, either into the bright regions, as illustrated above, or into the dark regions, to form the permanent grating, below. A special characteristic of volume gratings is that their optical functionality can be attributed to very small modulations of optical properties inside the holographic material. In case of phase gratings with a layer thickness of 200 micrometer, a refractive index contrast in the order of only 10:3 already results in diffraction efficiency close to 100%. The contrast of such optical structures can be further enhanced with additives such as nanoparticles or quantum dots. It can also be combined with other mechanisms such as photochemical isomerization of optically anisotropic components or with polymer dispersed liquid crystals, PDLCs, for switchable or tunable optical devices. Furthermore, the light-induced mass transport may result in the formation of additional surface relief gratings. First of all, a photosensitive medium for volume holographic recording must be capable to undergo molecular or structural transformations with the result of a local, and in most cases, permanent change of the optical properties, as described in the previous section. In addition, and with focus on the functionality of volume holographic gratings, the medium must comply with high material standards. In this context, a number of material parameters must be optimized, namely sensitivity and dynamic range, resolution, transparency and stability. The following table gives an overview of important material parameters for volume holographic recording. Indispensable prerequisite for the material composition is the ability to form stable layers with thickness in the range of at least 50 micrometer where a refractive index contrast delta N in the order of 10:3 can be induced. The material resolution U refers to the precision within the ability of a photosensitive material to transfer the interference pattern of exposure into a permanent modulation of optical properties during the recording process, depending on the smallest structure size of the exposure pattern. It is therefore related to the precision of the final recorded structure. With the objective to fully exploit the interference pattern of the exposure beams, high material resolution is required. With regard to the maximum spatial frequency response, that is, the highest frequency inducing a permanent refractive index modulation, a value in the range of 5,000 to 10,000 lines per millimeter is aspired. The sensitivities provides information on how the input energy is converted into a certain holographic contrast. High sensitivity is required with respect to the possible application of low-power laser sources but also to ensure high recording speed. In this context, the dynamic range m# refers to the total response of a medium, when divided up to n holograms. It determines how many holograms can be multiplexed in a single volume. Highest transparency of the material at the operating wavelength is required to achieve high diffraction efficiency. Low attenuation becomes particularly important in case of thick layers, desired for volume holographic applications. In general, losses arising from absorption and scattering should not exceed 30%. Although much lower values might be required, depending on the layer thickness, for certain specific applications. Next to a high sensitivity, high spatial resolution and low losses, a high thermal stability and long-time stability of samples and systems are required. Altogether, the diversity of material requirements is accompanied by a diversity of approaches to meet these needs. The range of photosensitive media used for volume holographic recording is as diverse as the spectrum of potential applications. Although photographic emulsion, the original holographic recording material, is capable to form amplitude as well as phase holograms with good sensitivity and stability as well as high spatial resolution, it nevertheless appears inappropriate for volume holography. This is due to the fact that the sample thickness is limited to only a few microns, a serious disadvantage in view of the aspired recording of thick gratings for volume holography. Photosensitive polymers have been used as holographic media since 1969. Polymers combine many advantages, namely low cost, ease of fabrication, flexibility and the ability to be integrated in more complex systems, such as optical circuits. They fulfill the requirements for volume holographic recording with no need for solvent processing, good dimensional stability, variable thickness, high energetic sensitivity, large dynamic range and sharp angular selectivity. Among polymers for volume holographic recording, there are two material classes, differing in the mechanism of polymerization. The performances of free radical, FRP, and cationic ring opening polymerization, CROP, systems differ in many respects. Ranking among well-known FRP systems, glass-like polymer based on polymethyl methacrylate, PMMA, with distributed phenanthrene quinone, PQ, is known as effective and thermally stable holographic recording material. Results on volume gratings within this lecture are based on investigations on gratings in free surface epoxy-based polymer samples, prepared by Microresist Technology GmbH. High performance is achieved in volumetrically stable, free surface samples with variable layer thickness. The corresponding mechanism of polymerization is a cationic ring opening polymerization. Similar to polyvinyl alcohol/acrylamide, PVA/AA, material, grating formation occurs primarily as a consequence of photopolymerization and mass transport processes. Photorefractive materials, such as lithium niobate, barium titanate or gallium arsenide, are capable to form temporary, erasable holograms as a result of a nonlinear optical effect. Recorded data may be erased by flooding the crystal with uniform illumination. Improved properties with respect to the dynamic range, sensitivity and signal-to-noise ratio have been demonstrated. Drawbacks are partially slow response time and low stability. Volume holographic gratings can be categorized according to different criteria. The following section gives an overview on the different types of gratings, and how they can be distinguished with regard to their optical functionality such as diffraction efficiency and angular response. With regard to the modulated optical property, phase gratings can be differentiated from absorption gratings. Depending on the physico-chemical processes involved in the grating formation, the diffraction efficiency can be attributed to a refractive index contrast and or to a modulation of the absorption, respectively. However, both can also be observed together. In this case, the modulation of the refractive index yields a part of the total diffraction efficiency while the absorption modulation induces additional diffraction. As a consequence, it is not possible to distinguish between phase and absorption gratings, based on the diffraction efficiency. Nor can such information be derived from a microscopic image. However, it may be provided from local analysis of the optical properties, namely refractive index and absorption, respectively. The dimensionality of a volume holographic grating indicates in how many spatial directions the modulation spreads.